Hello, everyone. My name is Dr. Sidra Jamil, and today I'm here to host a session for the spring series or session series of WEmpower Pakistan. Today I'm here to host a session of Dr. Uzma Hera. She'll be delivering a lecture on thermoelectric oxide materials for harvesting waste heat into electricity. Dr. Uzma Hera is working as assistant professor physical chemistry at the University of Punjab, Pakistan, Lahore, Pakistan. She received her PhD in chemistry in 2019 from Lahore University of the Management Sciences, LUMS, Lahore, Pakistan. She completed her MPhil physical chemistry in 2014 with distinction and MSc chemistry in 2010 from University of Peshawar, Pakistan. Her research interests include synthesis, characterization, and applications of perovskite oxide materials to address challenges in sustainable development, energy conversion, thermoelectrics, water splitting, photocatalysis, and energy storage. So over to you, Dr. Uzma.
Thank you, Dr. Sidra Jamil, for a very nice introduction. So I think there is no participant except you and me, and I think I'm going to start. If anyone will be there, will join us. Okay, so let's share my screen.
Yeah.
So, good morning to everyone, and I think this is the last lecture for WeEmpower Mentor Spring Lecture Series 2023. And the topic for my lecture is thermoelectric oxide materials for harvesting waste heat into electricity. And hopefully you will take some knowledge from this lecture. And so I'm going to start this lecture. So I will discuss about the thermoelectricity, and I will talk about thermoelectric oxide materials, and I will talk specifically about bismuth-topped strontium cobalt-ruthenium oxide system. And I will explain in detail about the crystal structure and microstructural analysis. Sorry. And I will also explain about the thermoelectric and thermal properties for these oxide materials. And at the end of lecture, I will explain about the figure of merit for these materials. So let's start, like why we need thermoelectricity. You can see 66% of the energy from different primary energy resources like automobiles, natural gas, thermal power plants, and nuclear power plants is dissipating in the form of waste heat. So it is very important to harvest and utilize this waste heat. We are only using 34% of the energy for useful purposes. So it is important to capture this waste heat. So what could be the possible solution? Thermoelectric could be the possible solution to capture this waste heat into electric power. So we will see that how we can use this concept for production of electricity. So thermoelectricity basically involves the concept which is given by the T.J. Seebeck back in 1821, and this is the diagram of the thermoelectric couple. You can see when we apply the waste heat across the couple, which consists of the P-type and N-type materials. When the waste heat will be applied, then these charge carriers start to move from the hotter junction towards the colder junction. And this movement of the charges will actually result in the production of voltage difference, which actually leads to the production of electrical power. If we reverse this process, then it results in the production of the cooling effect, which is called the Peltier effect. It means the thermoelectricity gives us two phenomena. One is the power generation, and another one is the refrigeration. And here our target is to produce the electrical power. So I will focus on the power generation for thermoelectric materials in this lecture. So for thermoelectric materials, it is very important to understand this equation, which is Gt is equal to F square sigma over K total T. Actually, we can explain the efficiency of thermoelectric material by using this figure of merit ZT. If you can see here, S is basically the Seebeck coefficient, and the sigma is electrical conductivity, and K is the thermal conductivity. So if we further see this S Seebeck coefficient, which is basically inversely related with the carrier concentration. If we will increase the carrier concentration, it means the reduction of the value of Seebeck coefficient. And if you see, this electrical conductivity is actually directly related with carrier concentration here. And thermal conductivity is actually the sum of electronic part of thermal conductivity and latest part of thermal conductivity. If we will further see, this electronic part of thermal conductivity is further related with carrier concentration. And here is the power factor for the material, which is actually the S square sigma. For practical purposes, this ZT value should be equal or greater than 1. So it means we need to increase the S and sigma and to decrease the K, which is basically the thermal conductivity. But you can see S and sigma are interrelated with each other. So it is very difficult to tune together both the S and sigma, because one is inversely related with carrier concentration and another one is directly related. So we need to focus on the thermal conductivity part to improve the ZT value for thermoelectric materials. So we will see how we can improve this ZT value. So if we have a look in the literature, up to now, a large number of thermoelectric materials have been investigated so far, which includes like the alloys materials and the half-oscillator compounds and scutterite compound. Although these materials have good CT value, but still there are some drawbacks are associated with these materials. As you can see, the constituting elements for these compounds are very toxic, and they are not available in abundant form, and they also have stability issues at high operating temperature. We need thermoelectric materials which can work with stability at high operating temperature. So I think oxide materials could be the possible solution to use these materials instead of these conventionally reported thermoelectric materials. These, as you know, the oxide materials have good thermal stability at high operating temperature, and their constituting elements are also non-toxic and inexpensive, and it is easy to fabricate these oxide materials. But the issue with these oxide materials is that they have a low ZT value. So we need to play with the thermoelectric properties to increase the ZT value. So we will play the structure of the material to improve the ZT value. So if we have a look in the literature again for thermoelectric oxide materials, most of the cobaltite material have represented the good ZT values. As you can see, all of these three materials are the P-type materials for high temperature thermoelectric application, and their single crystal ZT values for their single crystal compounds are good for high operating temperature, and you can see some decent numbers for these oxide materials. But still, we need a polycrystalline material, bulk material for practical purposes. So we need to play with the fabrication methods and the substitution methods to improve the ZT values for these oxide materials. So I have worked specifically on the perovskite materials. So first we need to understand about what is the perovskite crystal structure. These materials were first reported by the Leprovsky in 1839. Those materials have the crystal structure similar like that of calcium titanate are called the perovskite material. In perfect symmetry, they have cubic crystal structure and they are represented by the general formula AbO3 type. In this AbO3 type, this A mostly comes from the alkaline earth metals, and B is mostly the transition metal, and O is oxygenated. If we can show the one of the representation of the crystal structure for this type, you can see the A is present at the corner of the cubic unit cell, and B, which is basically the transition metal, is present at the center of the this cubic crystal structure. And you can see the oxygen is present in red sphere at the faces of the this unit cell. And you can see this oxygen is basically forming the octahedral crystal structure around the B transition metal. So I have worked specifically on the double perovskite oxide materials, and these materials are represented by the A2B B prime O6. You can see A is mostly the alkaline earth elements, or they can maybe the lanthanide elements from the periodic table, and this B is basically comes from the 3D transition metals from the periodic table, like manganese, cobalt, iron, and nickel, etc. And B prime is mostly the 4D and 5D transition metals like ruthenium, molybdenum, rhenium, and tungsten, etc. And these B and B prime actually alternate in the crystal structure. As you can see, this blue and yellow octahedra is repeating in the crystal structure, which actually producing some properties in the crystal structure with respect to their crystal structure. So, as you know, properties are directly linked with the crystal structure. So these ordered perovskite pattern is result in the formation of the better properties in the material. You will see in the coming slide that how the crystal structure basically affect the properties of the material. So different methods can be used for the fabrication of the oxide materials for thermoelectric point of view. And here I will focus on the solid state synthesis method. In this method, we usually take some stoichiometric amounts of the oxide materials. We will grind them and make a pellet and heat them at high temperature for some time. And again, we will repeat this process of pelletizations and heating, and until we will get the phase pure crystal structure for this material. As you know, like thermoelectric properties is basically the electrical transport properties and thermal transport properties, which is basically depend on the purity of the material. So we should have the phase pure crystal structure for these materials. So we will check the purity of the materials with XRD analysis, and we will stop the heating when we are sure that our material is phase pure after XRD analysis, and this material is ready for further analysis for thermoelectric applications. So I have prepared the series of bismuth, doped strontium, cobalt, ruthenium oxide, double oxide materials. As you can see, these are the XRD patterns for this material at room temperature. And you can see that all of the peaks could be indexed for this material and orthorhombic unit cell, and within the space group IMM symmetry, which is indicating that our material is pure and there is no impure phases present in our material. So this material is ready for further analysis. So these are the ritual refinement analysis of the XRD diffraction data, and you can see the nicely fit of the model with this within this space group like IMM, and which is indicating that our model is perfect and it is following this orthorhombic crystal structure symmetry. And here you can see that difference line is almost the straight, which is indicating that our experimental data is completely fit with our model. So we have extracted a large number of the parameters from this refinement data, and these are the latest parameters which we have extracted from the refinement data. And you can see that all the latest parameters A, C, B, and unit cell volume V is increasing with increasing the doping contents. As you know, we are doping bismuth at the site of the strontium, and the ionic radius of the bismuth is smaller than the strontium. So technically, our unit cell is going to expand, although the ionic radius of the bismuth is smaller than strontium. So what could be the possible reason, like why our unit cell is going to expand? So one could be the possible reason that in case of B, we have the lone pair of electron on the bismuth. So it could be result in the distortion in the unit cell and expansion of the unit cell. So this is the crystal structure we have drawn from the Vista software by using the XRD data, and you can see the this is the this green is the strontium side, and you can see the tinge of purple, which is indicating that bismuth is going inside the crystal structure at the strontium side, which is basically the A side of the perovskite material. And these octahedra are the in one is the cobalt and another one is the ruthenium. these are alternating within the crystal structure. So it means our dopant is going to sit inside the crystal structure of the material. So this is a good sign, like we are going to achieve for our dopant to exactly sit down at some points in the unit cell. So these are the scanning electron microscope images for this material. As you can see that the grain size is continuously is increasing with increasing the bismuth content, and you can see when we are going to increase the bismuth dopant, it results in the increase of grain size. So it means the boiling point of the melting point of the bismuth constituting elements is smaller than the strontium carbonate, which results in the increase of the bigger grain size development within the increase of the dopant. And this is the electrical resistivity data for this series of material. And you can see the electrical resistivity data has a function of temperature. And the curve you can see is representing our material is semiconducting type of material, because the electrical resistivity is decreasing with increasing temperature. And you can see further with increasing doping content from 0.2 to 0.8, the electrical resistivity is further decreasing. It means that bismuth is producing more carrier concentration in our system. And we have applied the small polaron hopping model on this electrical resistivity data, and it goes the nicely fit with these data. And we have calculated the activation energy from this data, and you can see the activation energy is decreasing with increasing bismuth content, which is indicating that less energy is required for hopping the electrons from valence band to the conduction band. And this is the Seebeck coefficient data has been taken as a function of temperature, and you can see for the pure compound, our Seebeck coefficient is increasing with increasing temperature. And here is also, you can see some interesting fact that the Seebeck coefficient values for the pure compound and with the small dopant sample is in negative values, while the values are going towards the positive side. So it means when the values are negative, our material is p-type material. And when the S values are positive, it is indicating that our material is p-type material. It means our material is changing within the dopant from p-type behavior to n-type material. And as you can see in our introduction slides, that we need both p-type and n-type material for thermoelectric module. So it means with this series of sample, we have both p-type and n-type material. And small polaron hopping model is also get nicely fit with the Seebeck coefficient data, and we have also calculated the activation energy from the Seebeck data. And you can also see the same trend of this activation energy from Seebeck data is decreasing with increasing the bismuth dopant. And here you can see that these numbers is we also have obtained the number for activation energy is smaller for Seebeck data. Then the activation energy is calculated from electrical resistivity data. So we have calculated the power factor from using the Seebeck coefficient and electrical resistivity data, and you can see with the highest dopant sample, which is the 0.8, we have got some nice value for power factor values at the high operating temperature. It means the dopant is going to work well for thermoelectric point of view in terms of power factor. So further, we have calculated the thermal properties by calculating the thermal conductivity as a function of temperature. And you can see this thermal conductivity is increasing with increasing temperature, and these values are also going to increase with increasing temperature. So, sorry. So at the end, we have all these three properties like Seebeck coefficient, electrical resistivity, thermal conductivity, and we have calculated the ZT value by using these three parameters. And you can see our pure compound has very low ZT value, and but with the highest dopant content, we have obtained the maximum ZT value, which is greater than 0.10. Although the ZT value is not good from the commercial point of view, but still this material is showing some room for thermoelectric application. So there is a need to work more on this material, that how we can tune the ZT value for improving its thermoelectric figure of merit, because for practical purposes, we should have ZT value greater than 1. And so we need to prepare our samples by using some more good techniques like spark plasma, centering, and hot pressing, because here we're going to prepare the sample by just using the normal pressing technique. So there is a room in this material, and it could be the potential material for thermoelectric performance. And we are also working currently, and also have a plan to work in future on this material for improving further its CT value. So we can conclude our lecture that we were successful in preparing the single phase material by using the solid state synthesis method, and we have completely done the crystal structure analysis for these double peroxide materials, and we concluded that our dopant, which is basically the bismuth in this case, is going inside the crystal structure and changing the crystal structure by using the XRD pattern and the latest parameters and the other parameters we have extracted from this data. And it means when bismuth is going inside the crystallographic crystal structure, it also results in the affecting the properties of the materials like electrical conductivity, Seebeck coefficient, and ultimately leads to the improvement of the power factor. And at the end, it gives the nice value for thermoelectric efficiency. So these are the all points from my lecture today. If anyone has question, can ask. Or anything you want further explanation or justification from this lecture.
Thank you, Dr. Uzma, for the wonderful lecture. But as you know that we don't have any participants, so I can only ask you some questions,
Yes,
which
yes,
I
please.
have
Sure.
from your, yeah. First of all, I want to ask you a question. That is, you have mentioned that thermoelectric material have application in energy storage and conversion as well. So I'm also working on batteries. So can you be able to relate that how can this material be able to apply to the energy storage or conversion process? Like
Uh,
in which particular?
Actually, I can give you an example. Like we are using the stove here, like for cooking purposes. So we are also
Yeah.
producing dissipating heat. If we produce the electricity by connecting some module, a thermoelectric module, to recycle this waste heat of the stove into electrical power, and also we can connect this module with some batteries. And at the same time, we will also use this electrical power in the for storage purpose.
Oh, yeah. That's good. That's good. And another question is you're focusing more towards the oxide materials, right? But recently I have been looking at the papers like sulfide and selenides are also uh, like sulfide and selenide materials are also using as thermoelectric materials. So what would you prefer, whether the sulfides, selenides, or the oxides? Which one would have the better thermoelectric performance if we
If
need to
we
select?
talk, yes, yeah, this is a good question actually. And if we talk about in terms of the efficiency, the salinide and sulfide materials have good thermoelectric efficiency, right? They have better GT values. As I also mentioned in my introductory slides, that alloys and these compounds have like bismuth, salinide, and telluride have good ZT values. But again, the problem with these material is that, like, they're constituting elements like selenide and bismuth and tellurium. These are the toxic metals, and they are also not available in abundant form. And the second
Mm.
thing, we need these thermoelectric properties for high operating temperatures. And these elements are not stable at high operating temperatures because these elements are volatile. So these elements are not good for high temperature application. But if we talk about in terms of stability, the oxide materials are very good, because most of the oxide materials are stable even at 1000 Kelvin temperature and more than 1000 Kelvin temperature, like aluminum oxide and calcium cobalt oxide. But the problem with the oxide material is their efficiency problem. In terms of efficiency, they're not good. So still there is some work is going on oxide material to improve their efficiency for high temperature thermoelectric applications.
I got it. Thank you so much. Thank you.
Welcome, you're welcome.
So, do we have another question? I think so. No.
One participant has joined, but I don't know.
Yeah,
He has missed the lecture.
yeah, maybe. So I think we should leave the meeting. Is that fine?
That is fine for me, but if
Yeah,
anyone
okay.
has another question, can write me
Yeah,
direct.
anyone has another question, so we can answer, but I think so, no, maybe.
Yes.
Okay, thank you so much once again.
Thank you so much, Sidra.
Goodbye.
Goodbye.
Yes.